Hello everyone, welcome to my final presentation for NLP sentiment analysis for mental health states for my S89B course in natural language processing at Harvard Extension School. Now to introduce the raw data I used, we can look at the top left. With the key, there's two columns and the data, a statement, a text statement, and a status, mental health status, one of 7. So the statement data is sourced from diverse platforms, including social media posts, Reddit posts, Twitter, and more, and blogs. There are actually 51,074 unique statements and unique rows, and these are all labeled in the Kaggle dataset, which is where I source my dataset into one of 7 mental health statuses. And you can see the distribution of these status labels down here in the bar chart. So they range from normal to depression and more extreme, such as suicidal, all the way to personality disorder. And there are most normal posts with over 16,000 and very less than 2,000, so very few personality disorder posts. And the goal of this project is to combine the increased amount of social media text with the growing prevalence of mental health issues and use NLP and machine learning tools to understand these and discover these mental health status issues early from online text posts. And a note on compute and top words. So all code was actually trained on a MacBook Pro with an M3 Pro chip, which the full code takes around 2 to 3 hours to run locally. The 3 most computational intensive portions are KNN, since I used an optimized K-search. That takes upwards of 30 minutes. A linear SVM, which takes around 20 minutes. And optimal SVM parameter tuning was actually removed because it takes more than 3 hours just for a 2x3 grid search. So linear and polynomial with 3 parameter variants. And that was commented out in the code. And finally, a BERT model application, which takes around 70 minutes to train for 3 epochs, and which was enough, right? So if we remove most 3 computationally intensive portions, the entire code takes maybe within 30 minutes to run. And on the right, we see top 20 words by an TF-IDF frequency in a frequency bar chart / heat map. And so we get a very clear idea. The general type of text is everyday communication. All 20 words are mostly stop words, such as to, the, in, and they're very frequent English words. And so I realized early on in the project, if I take these out, it might slightly improve compute efficiency, but removing them actually might negatively impact the results, the classification accuracy, especially if the method takes into account of the text context, right? So I try not to remove stop words, although it's still used in certain methods. And now we look at some EDA analysis. First, we have a PCA visualization of the data with the 2 principal components. On the right, we see very clear different blobs of color, and there, for example, on the right here, there's some overlapping between the purple, yellow, and light blue. So these could be, for example, the light blue could be large regions of normal, and some normal people are anxious or depressed sometimes or stressed. And there's also very distinct regions of relatively independent regions of purple on the left. These could be more extreme, such as suicidal or people that are bipolar or have personality disorders. I also used TextBlob, the package, to create a polarity column and plotted the polarity with text length at the bottom left. And we see very clear correlation between different types of mental health statuses and longer text length. All the outliers above 10,000 words in terms of single posts are either suicidal, bipolar, or personality disorder. And so that makes sense because more extreme lengths have more extreme disorders. Now there's further EDA analysis. Here's first the box plot of polarity versus the mental health status. The data is actually very good, and we see normal is not the only category with positive polarity in its quartiles. There's also stress, bipolar, and personality disorder also shows clear positive polarity, and it's within its core sort of quartiles, which makes sense because some stressed people or bipolar maniac states will also have positive states at times. And suicidal obviously has the most negative and the lowest polarity as expected. And on the right, this violin plot just confirms what we saw earlier, that the most extreme outliers are the most extreme mental statuses, so suicidal and personality disorder. But we also see on average, for example, depression actually gives close to the relatively longest text with personality disorder. Now we look at some sample word clouds. Shown here is bipolar. Interestingly, just the letters M and S show up as single letters, which could stand for the two poles of bipolarity, mania and depression. Where depression also shows up, we see the word feel actually is common across all word clouds. Anxiety is not shown here, but for many of the word clouds, the status itself is in the word clouds. So anxiety, for example, anxiety, people type stress if they're feeling stressed. And for suicidal, we see here on the bottom right, most obvious tell is the word anymore, I don't want to live anymore, the word die. We also see the word life, love, live, world, so they're reflecting on the world and they perhaps are contemplating ending their life. And so I start with LDA topic modeling and coherence model. And so in the full LDA, I remove stop words, punctuations, and do some pre-processing to ensure irrelevant elements do not affect the topic modeling. And then a dictionary and corpus is created, representing actually each kind of statement as a bag of words. And the LDA model is trained explicitly with 7 topics to try and match the given statuses. The coherence score obtained is 0.518, which is not good but reasonable given the high frequency of stop words, which are removed in the data. Exclusivity scores from different runs range from 0.8 to 1.0. We see in this case it's 0.9 to 1.0, which is very high, but still makes sense given the distinct 7 status labels, right? And looking at the topics, that actually makes more sense. For example, in this particular run, let's look at topic 1, for example. The word depression, so depression is in topic 1, so that is depression, right? And if we look at these more closely, we can do an elimination one by one, and eventually we can figure each one out. So in an earlier run, topic 1 had beer and cannot take it anymore, which is obviously stress. The word anxiety in topic 2, the word bipolar in topic 3, depressive words in overall topic 4, can't live in topic 5, which is suicidal, very normal words in topic 6, and very weird personality disorder words such as homosexual, inferior in topic 7. So it's actually very clear, and it confirms that the exclusivity scores, albeit high, probably do make sense here. And so I start with variants of logistic regression. Initially, I run a bag of words using a cat vectorizer with 5,000 features max, and applied the vectorized data to a very simple logistic regression. Shows that the confusion matrix here shows that the classifier performs well for majority classes. So the classes with the most data, for example, normal, right? It has 3,000 classified correctly, 3,107 here, and very little, less than 100 for the others. However, very small categories, for example, bipolar and personality disorder, show similar numbers of misclassified statuses, and that's a much larger ratio of misclassified statuses, and that has to do with the class imbalance, right? That's an insight we get initially. And so here's a more detailed classification report, and I actually ran logistic regression with various vectorization techniques and NLP techniques. And one of the best performing ones here was TF-IDF with an n-grams 1 to 3. Adding n-grams into this mix, actually the overall performance was exactly the same to the one above, which is shown just the TF-IDF vectorization and logistic regression. So there was actually not much improvement, very slight variations in the specifics. We also see again here that smaller categories such as stress, suicidal, personality disorder with less support tend to perform slightly worse, although there is not a clear one-to-one correlation either if we look at the entire classification report. And here I summarize all the machine learning methods I used. which is 6 with different variants. So logistic regression, naive Bayes. I ran a KNN with an optimized K-search, which actually resulted as 1 in this case, which makes sense as we just look at the nearest neighbor, right? It happens for many classification problems. Simple SVM or linear SVM, random forest, and decision tree. And I made some notes about the random forest here because I expected it would perform well, but there's actually a lot of variance in its accuracy, precision, an F1 score. And upon details look, the parameters I probably should have further tweaks. I didn't set a max depth. I probably should to prevent overfitting, which I thought might likely occurred in this case given the class imbalance data, as the normal is much overrepresented. This also explained the much higher precision versus accuracy shown here, because true positives can be predicted overall, but true negatives are easily missed when you have a class imbalance. And overall, we see that the logistic regression using the TF-IDF with 1 to 3 n-grams mentioned earlier, as well as the linear SVM performed best, with accuracy and F1 scores reaching above 0.75 to 0.76, 0.77. And then I moved on to neural network applications, a very simple neural network, starting with the parameters here, 2 dropout layers, 50% each to prevent overfitting, max features of 10,000. To expand, since I thought 5,000 might have limited the results earlier. And we see very clear optimal kind of epochs of around 4 to 5 before we start overfitting. And the validation accuracy maxed out around 0.78, 0.77. And I tried to improve on these neural networks. So I used various methods we covered in this course, using standard spaCy, incorporating NER labels for enhancement, using small batch sizes, playing around with the hyperparameters, smaller dropout rates, more progressive layers, etc. And after all that tweaking, there was not much improvement, and often runs, as we see on the right, the overall score is actually decreased. And so my takeaway here is that this may indicate limits with the data set itself. Certain categories are much harder to predict. For example, as we see here, stress again is a very low F1 score, below 0.6 for the neural network, similar to all the classical machine learning methods. And even normal is only predicted with near 90% accuracy, because there's natural variance in text that's not purely mental status focus. It's just normal everyday text. And finally, I ran a BERT model, BERT based on case, so that's the same one we used in assignments, and tokenized the data with 120 and max length, etc. And the results are best by far. The accuracy reached 83.44% on validation data. Recall was also above 0.8. This made sense given the extensiveness of the Google BERT and the architecture, the bidirectional encoder-only transformer architecture, still very relevant today, even in our post-GPT world. And there's also finally an afterword of top 20 predictor words, which I printed out here, and top features. And the predictor words made sense here. I made a comment. Some of them are actually very unique. This is from the neural network. So ripped, holiday, limit, unfair, fasting. They seem to be unique, but also mentally status related words. And comparing the top features for each category, which I left at the very end as the last piece of EDA, there's definitely some overlaps. This is the word "oi" we see here. Very simple word. But mostly they're actually very independent and specific, as top features are for each category and not overall. And so finally, the overall project conclusions, as we saw from PCA plotting, clear traits of separation and overlap of the 7 statuses, which made sense from box plots, the scatter plots, VLN plots, polarity, correlation between text length and the statuses. And topic modeling showed that the 7 statuses have very high exclusivity scores, confirming the EDA analysis. For classical machine learning, we tried 6 different methods and variants, and best ones were SVM and TDF vectorization with n-grams, and applied to logistic regression. And they come out to 0.77 optimally in terms of accuracy. And the worst performing methods had troubles with certain categories such as stress, which had smaller sample sizes, so smaller support, right? The NLP enhancement methods were shown to improve accuracy slightly, but not make a huge difference, as the overall range among these methods is not too large. In neural network applications, hyperparameter tuning and NER actually did not significantly improve the text accuracy, again reaching 0.77, 0.78. Similar to classical machine learning methods, the best of them. And finally, BERT was applied, and we got an accuracy of 0.83 and a recall above 0.80 as well, which is by far the best model found, and made sense given the sophistication of the model architecture. So I learned here that sometimes results qualities are limited by the problem definition of the data itself. And obviously, just using everyday online posts, it might not be able to perfectly classify mental health statuses, and there's some subjective interpretation, I would imagine, to the labeling as well. So all in all, NLP methods combined with machine learning is very insightful in assessing the mental status of text, and the predictive methods here can be applied in real-world psychology settings. Thank you.